Hello, everybody, and welcome back to another lecture in Geography 340, Climatology. My name is Dr. Zach Hilgendorf, and today we're going to be talking about Earth-Sun geometry, kind of playing off of our last few lectures focusing on solar radiation. And then going on from here, this is going to be a bit of a shorter video to set up our next video, which is going to be on the seasons and why we have seasons here on Earth. So we're going to start off here just discussing the two basic motions of our planet. First, we have rotation, so the spinning of Earth on its axis. One rotation equals 1 day on our planet, right? It's just how the Earth rotates once or throughout a year. The second is orbit or revolution, where the Earth is moving around the sun. So that takes place on a much longer time scale, 365.25 days on Earth. That's why every 4 years we have a leap years to accommodate that extra quarter of a day in our calendars. So the Earth rotates on a slight elliptic orbit, meaning that it's slightly oblong versus perfectly circular. We'll see that here in this next slide. So each year as the Earth spins on its elliptical orbit, it reaches its orbital minima around January 3rd at a distance of roughly 147 million kilometers from the sun. That means the Earth is closest to the sun around January 3rd. This position is called the perihelion. 6 months later, around July 4th, the Earth reaches its orbital maxima at a distance of 152 kilometers from the sun, position called the aphelion. A-P-H-E-L-I-O-N, aphelion. Earth receives roughly 7% more energy in January than July, but this difference plays only a really small role in producing seasonal temperature variations. So here we can see the perihelion and aphelion positions, here and here. Next, notice the opaque plane that makes up the Earth's orbital plane. This is known as the ecliptic plane, or plane of the ecliptic. Notice that it is an elliptical. It is not perfectly circular. Now, despite Earth orbiting on a consistent plane, as we've seen here, we learned that the energy difference between the perihelion and aphelion positions only constitute about 7% of Earth's incoming solar energy. So in this video, we're going to stop short of fully describing the seasons, but we're going to set up the concepts here. So first off, we should talk about axial tilt and axial parallelism. So while there can be no definitive answer because no one was there to actually watch it happen, it's thought that sometime very, very long ago, something hit the Earth and essentially knocked it off kilter, so to speak. Following this event, instead of rotating on its axis perfectly up and down, it got a lean, it got a tilt in its axis. So as a quick aside, it's actually thought that this large impact event is probably what led to the formation of our moon, which is pretty awesome. But that's how the Earth is thought to have developed its tilt. The poles aren't perfectly up and down, as we'll see here in these next couple of slides. So axial parallelism refers to the fact that the axis of Earth remains parallel to its previous position as Earth revolves around the sun. This means that Earth's axis always points in the same direction. We can see axial parallelism here. Notice how along the ecliptic plane, which is that circle in the center there, the axis is always off roughly 23.5 degrees from center, no matter where it is along that plane, whether it's in any of the solstices or equinoxes or any time in between. So let's make a diagram of our Earth and some of the things that we're going to be interested in about. So first off, we can see that horizontal line or perpendicular to the sun line, the ecliptic plane. Next, we can see an imaginary line connecting our north and south poles. After that, we can see the equator bisecting the planet midway between the north and south poles. Notice it's not on the line of the ecliptic plane, it's in relation to our poles, our true, north, if you will. So this points at 0 degrees latitude, where the poles are at 90 degrees north and 90 degrees south latitude. Next, notice that black line in the center of the planet there. The hemisphere that is illuminated and the hemisphere that is shaded, our day and our night, are separated by the circle of illumination, not the sphere of illumination. That circle is just a two-dimensional circle around the planet that separates the zone of illumination from the zone of shading or shadow. Next, we have these two corresponding angles. So these angles represent the offset between the line connecting the poles and the circle of illumination. They're always equal to 23.5 degrees. These angles represent the degrees between the ecliptic plane and the poles and are always going to equal 66.5 degrees. If you do your quick math, 90 degrees. So this is just one way we can look at the Earth. In our next video, in the seasonal one, we're going to talk about when and during what times of the year we care about where the sun is pointing and the kind of that subsolar point and the angles of declination that we talked about in our last video to better understand how we define our seasons. So just to recap, we talked about the movements of Earth, its rotation or orbit, or revolution, if you will. We talked about the different components of that orbit, the ecliptic plane, the perihelion, and the aphelion, and we talked about the characteristics of its axis. In our next video, we're going to be talking about the seasons. So appropriate because as I look out, it is a beautiful October afternoon, and we just crossed over into fall. So I look forward to seeing you all in the next video, and I hope you have a great day. Thank you.